We started a new unit on dynamics last week, and we defined dynamics as a study of motion, almost like kinematics, but this was the study of motion with regard to what causes the motion. And what was it that caused the motion? Yep. It was forces that caused the motion. Good. What's a force? What do we define a force as? Venture, what did we define a force as?
A push or a pull.
Good. Good. A force is defined as a push or a pull. Now, that's not to be confused with the two things that a force can do. What is it that a force can do, Max? Okay, so it can cause an object to accelerate. Now, when we cause an object to accelerate, we include with that speeding up, we include with that slowing down, we include with that changing direction. Bottom line is, when something changes velocity, and velocity includes both magnitude and direction. So when something changes velocity, speeds up, slows down, or changes direction, it accelerates. And that can happen, or that will happen, because of a force, a net force that's applied to something. And the other thing was, we can deform something. We can change the shape of something. Is there ever a situation where we can change the shape and accelerate an object? Of course there is. When we bounce a basketball on the floor, we change the shape of the basketball, at least temporarily, but we also accelerate the basketball. When a car comes to a crashing stop because it collides with a cement wall or collides with some other car, it gets deformed, its shape changes, but it also usually decelerates. In some cases, it could accelerate or speed up if it's hit from behind. Good. Net force. Net force. Luke. Good. Net force is the unbalanced force, or the total force that acts on an object. And we use the analogy of my net salary, or your net salary when you get your pay stub at the end of the month, or at the end of the 2-week pay period, or whatever it is. Net is total. When we add up all of the money that we get and get taken away from us, the positives and negatives of the money that are on my pay stub, that's my net salary. The positives and negatives of the forces, when we add them together, that's my net force, or my total force. Good. Now, this one gets a little bit trickier here. Inertia. Inertia, Caitlin.
Tendency of an object to resist a change in motion.
Good. We want to resist motion, right? Everything wants to resist motion. An object at rest wants to resist motion, resist a change in motion. Hey, if it's at rest, it wants to stay at rest, wants to keep doing what it's doing. An object that's in motion wants to stay in motion in a straight line at a constant speed because it wants to resist a change in motion. Now, what does that term equilibrium mean? Regardless of the context, static or translational equilibrium, Megan?
Kind of like a balance.
Yeah, equilibrium in general means kind of balanced, right? And in the context of physics, we're talking about balanced forces. So when we're talking about balanced forces that are static, we're talking about an object that is at rest, an object that's at rest with balanced forces. So what does an object that's at rest with balanced forces end up doing? Balanced forces, or we could say what's the other term that I could use there? Balanced forces or Tiana? No net force. Good. No net force. So if an object is at rest, static, with no net force or no unbalanced force, then what's going to happen to it? Yep. Good, Ariel. It's going to stay at rest. It's going to stay at rest. An object at rest wants to stay at rest. Now, there is a way that we can get that moving, right? There is a way that we can keep it from staying at rest, that we can change its motion, and that is to apply a net force, an unbalanced force to it. But as long as there's no unbalanced force, an object at rest is going to stay at rest. Translational equilibrium talks about an object that's moving that has balanced forces on it. If we have balanced forces, or what's the other term again? No net force, right? Do you know? No net force acting on it when it's moving, then that means that it's going to keep moving. And in the end, it ends up keep moving at a constant speed in a straight line. Yesterday, when I was going to my cross-country meet in Sundre, we had a Physics 20 student from the other class that was in the bus, and we went around a turn. We're on a turn going onto the highway like this. Okay, and of course, when you're going around that turn on the, everybody knows that off-ramp going onto Highway 2, right? Going onto Deerfoot Trail from 2A here, and you're going around that turn, and you kind of get pushed to the outside of your car, right? Like when you're turning, you kind of get pushed over. Well, you're not really getting pushed over. What you really want to do is go in a straight line. You feel like you're being pushed over, but really what you're doing is going in a straight line. And you end up going in a straight line because there's no net force acting on you until basically your body hits the side of your door, or until the seatbelt holds you from going in a straight line. An object in motion wants to go in a straight line. Okay? This car or this bus that's going around the turn here wants to go in a straight line until acted upon by an unbalanced force. That's translational equilibrium. Now, Newton's first law kind of puts all of this together. Newton's first law says two things. Well, it talks about static equilibrium and it talks about translational equilibrium. The first part of it says an object at rest will stay at rest. Right? It's the static equilibrium. An object at rest will stay at rest until what? Who's up? Okay, until what? Good, until acted upon by an unbalanced force. Or in other words, until acted upon by a net force, by a total force that's not zero. And the other part of it, this is the whole translational equilibrium thing. Another part of it says an object in motion will, what's it going to do? An object in motion will? An object in motion is going to, good, will stay in motion until acted upon by an unbalanced force, or until acted upon by a net force that isn't zero. Now we're going to add a little bit to this. Not only is it going to stay in motion, it's going to stay in motion in a straight line. Remember, there's two things that a force can do, that a net force can do. It can cause an object to accelerate, which includes change direction. If you don't have a net force, it's not going to accelerate, which means it's not going to change direction. So if it's in translational equilibrium, it's going to keep going in a straight line. But it's also not going to cause it to speed up or slow down if you don't have a net force. If the forces are balanced, it's going to go in a straight line at a constant speed. When I was 16 years old, I used to drive a delivery van for a dry cleaning company. And greatest job in the world. I love driving. And so that was the greatest job in the world for a 16-year-old kid that loves to drive. And I remember that this one day I had to make this run from the dry cleaning plant to the airport terminal, which is about 45 minutes away. And I remember coming off, there was some snow and some slush on the highway and whatever, and I was 16. I had my driver's license for maybe about 6 or 8 months, and I was a pretty good driver, but still inexperienced at 16 years old. And I remember going off the highway, which was fine. I was going about 100 on the highway, which was absolutely fine. Then I go off the off-ramp, which normally, like, you hit the slow down lane in the off-ramp, okay, and that's when you start slowing down and you get to the turn. Sometimes you're going a little bit faster on the turn, right? But it's fine. You end up making it around. Well, this time I didn't. Okay, this time, the only time I've ever been in an accident, actually, that I've been driving, and it wasn't bad, but I was driving. Here's the highway. Here's the off-ramp like this, and then the off-ramp curves around and goes underneath the highway like this. So I'm driving, it's going fine, going around the turn like this. Now I start slowing down. Okay, but because of the slush and a little bit of ice on the road, what happens? Well, there was no friction. There wasn't very much friction on the road. So what happened to me? with no friction, with no unbalanced force, I was in translational equilibrium. And when I was in translational equilibrium, the net result of that was, what happened to my van? Yeah? I went in a straight line at a constant speed. Like this. Until an unbalanced force caused me to not go in a straight line at a constant speed, which ends up being the guardrail that's beside there. So the guardrail right there ends up causing the unbalanced force. Unfortunately, not the force of friction that was acting between the tires and the road, because there wasn't any, or at least not enough friction acting. Does that make sense? So we're talking about an object that's at rest, like you sitting at your desk. You're not going to do anything. Okay, you're just going to sit there until acted upon by an unbalanced force. Okay, if there's an earthquake, then you might fall to your desk, start moving. But until you're acted upon by an unbalanced force, you're going to just sit there. But an object that's in motion, like a curling rock, will keep going. A car that has no ice, or sorry, that has no friction, will keep going in a straight line forever until acted upon by an unbalanced force, which might be the guardrail, or it might be the ditch, or it might be a cow in the field over here, or something that provides an unbalanced force or a net force. We're going to give you a few minutes right now to work on a couple check and reflect questions on page 142 if you have your textbook downloaded. This is chapter 3, by the way. If you don't have a textbook downloaded, you want to download it, chapter 3, you should download now. Otherwise, you can just look off of the board, that's fine. 5 questions here, questions 1 to 4 and 6. Give you a few minutes to work on that. See if you have some time to work to finish it up in class. If not, you'll finish this up for homework and then we'll move on. Christian, give me an example. Give me one example, other than the one that we've talked about in class, that illustrates a property of inertia for either a stationary object or a moving object. So I don't care whether it's stationary or moving, just give me an example that illustrates inertia or the tendency to resist a change in motion for one of those two, one that we haven't talked about in class.
So if a car applies its brakes, the brake pads grab onto the brake disc to create friction, causing the car to slow down.
Okay, good answer. That's a great answer. Hey, if a car applies the brakes pads apply a force of friction on the discs, which that's the unbalanced force, right? That's the net force that causes the car to slow down. In the absence of that, what happens?
The car will go straight.
The car keeps going in a straight line at a constant speed until you put your foot on the brake, right? Until that unbalanced force acts. Good, good, excellent. Christine, give me another example of a situation that illustrates the property of inertia, either for an object in motion or an object that's at rest. Okay, I'll come back to you. That's okay. That's okay. I'll come back to you. Let's go Maddie G. Maddie G. Give me another example of a situation that is explained by inertia for either an object that's at rest or an object that's moving.
Like if you're throwing a ball, the ball's just going to go in a straight line until it's affected by something.
Okay, so you throw a ball, it's going to go in a straight line until it's affected by something. What's the most obvious thing that that ball will get affected by? Yep. Air resistance, yeah, it could be air resistance. Ryan? What's the other thing that's probably going to have a bigger factor than does air or air resistance? Yep. It's going to be gravity. Good. Gravity is going to have cause it to accelerate downward, right? Horizontally, we said when we did projectile motion, then an object goes at a constant velocity, right? In the absence of air resistance, that is, it goes at a constant velocity because there's no unbalanced force acting on it horizontally. But vertically, it accelerates downward at 9.81 because there is a force that acts on it vertically, and that would be gravity. Good. Yeah, you know what? Keep going. Keep going on these questions, and I'll ask you another one in a couple minutes, okay? 4B is a great question, hey? While moving at a constant speed on a level, snowy surface, a snowmobile throws a ball vertically upward. If the snowmobile continues moving at a constant velocity, the ball returns to the driver. So picture this, right? You're driving the snowmobile, and you throw the ball straight up into the air, but you keep going. But yet the ball returns to you. What does the ball land ahead of the driver if it stops. We're going to assume that the air resistance acting on the ball was negligible. So if I'm driving my snowmobile, okay, watch me, I'm riding my snowmobile, I throw the ball up, I keep going at a constant speed, the ball comes right back to me. But if I stop, then the ball lands ahead of me. How is that possible? How is that possible? Who haven't I got? Megan? Oh, I already got you. That's okay. I'll get you again here.
Well, because the snowball is technically traveling at the same speed as the snowmobile.
Horizontally, right? Yeah, good. So vertically, it's accelerating, it's slowing down and going and speeding up, right? But horizontally, which is the important one here, it's traveling at the same speed as the snowmobile. Okay, good. Keep going.
And so then, like, when you throw it up, it will go up and then it will almost be like a curved parabola.
It'll be exactly like a parabola. Absolutely. So if the snowmobile comes to a stop real quick, if there's an unbalanced force acting on the snowmobile, but there's not that unbalanced force acting on the ball, so it's going to keep going in a straight line, horizontally in a straight line, right? Let's draw a little picture of it here. Let's say that this is our snowmobile. Forgive my art. That's my snowmobile. And I throw a ball up into the air. Throw a ball straight up into the air. The snowmobile is moving, right? So what happens? If that snowmobile is moving at a constant speed, okay, a little bit later, the ball is like this, right? The ball has been moving horizontally at the same speed as the snowmobile, but vertically it's going up into the air. The snowmobile is over here now. The ball is up here. Snowmobile is over here. Well, the ball starts keep coming down, but it's still moving horizontally at the same speed as the snowmobile is. A little bit later, the ball is right here. It's still going with the snowmobile horizontally because they're both moving at a constant speed. Horizontally, vertically, of course, it's speeding up and slowing down. But if all of a sudden my snowmobile stops, if my snowmobile stops right here in position 2, then what happens? Well, the ball keeps going. And where does the ball end? Good. I got you here. It lands ahead of the snowmobile, right? And Megan said a minute ago that the shape of that path is it's a projectile motion question, right? It's a projectile motion question with an initial velocity that is in the y component, but also an initial velocity in the x component, which makes we have a funny angled question, right? Okay, we could treat that absolutely as a projectile motion question. Does that make sense? Good. Got you there, Jake. All right, let's move on a little bit here now from this whole inertia thing that we talked about last week. Expanded upon a little bit of it today, but we're going to move on to something different here now. Well, I should say extended. Not really move on to something different, but just extended. What does acceleration depend upon? There's two things. Erica, what's one of the things that acceleration depends upon? Time? Yeah, okay. You're right. Yeah, time and velocity. It does depend upon time and velocity, absolutely. Maybe I didn't ask that question well, okay? It absolutely depends upon time and not velocity per se, but change in velocity, right? Delta V. Okay? But what is it that cause the acceleration? Or not even what is it that cause acceleration. That would be part of this, but you'll see in a minute. Hopefully one of you guys gets my drift here, and we'll see in a minute here. Luke? Yeah. Okay, that's one of them. Okay, the acceleration depends upon the net force. We'll say number one is the net force. So clearly, the more net force you have acting on something, the more it's going to accelerate, right? You push something just lightly, it's going to accelerate. You push something with much, much bigger net force, then it's going to accelerate quicker, right? If you have a car that's driving down the highway and it hits a raccoon, well, there's a net force acting on that car caused by the raccoon, right? But it's not going to cause that much of a deceleration of the car. But if that car is traveling down the highway, it hits a moose instead of a raccoon, then the net force acting on the car is bigger, a lot bigger, which will cause a bigger acceleration, or in this case, deceleration of the car. So the amount of net force will certainly affect the amount of acceleration. What else? One more thing that I'm looking for here. One more thing that affects the amount of acceleration that we have. Directly. Okay, time absolutely does, okay, in conjunction with change in velocity, but they're the result of something else. So what is it that directly affects the amount of acceleration, besides the net force? Yeah?
Like the mass.
Good, the mass. How heavy something is. You guys remember what mass is, right? It's the amount of matter that's possessed by something measured in kilograms. If you apply, let's say you take that raccoon that applies a force on the car versus the moose that applies a force on the car, clearly the net force affects the acceleration. But if you take, let's say, a moose that applies a force on a car traveling down the highway, and a moose applying the exact same force on a semi-truck moving down the highway, which one accelerates more? Or decelerates more, as the case may be? The smart car or the semi-truck? Sorry? You end up getting the smart car accelerating more because its mass is less. Okay, the same thing goes the other way, right? You got a smart car sitting out in the parking lot, a semi-truck sitting out in the parking lot, and we get two guys together want to think they're funny, push this smart car across the parking lot. It's not going to be very hard to accelerate that smart car, right, with the force that those two guys can apply. But they have the same idea to try to push the semi-truck across the parking lot. It's much more difficult to accelerate the thing that has more mass. So we're going to say that acceleration depends upon, how much force you apply on it, but also how heavy it is, the mass of the object that you're trying to push. Now that's going to lead us into Newton's second law. First law, remember, objects at rest remains at rest, like you right now are going to sit there. Well, your hand was just sitting there too until you applied an unbalanced force on your hand that caused it to accelerate. An object at rest stays at rest until acted upon by an unbalanced force. An object in motion, I'm moving right now. Okay, I'm going to keep moving until I run into this stuff over here on the side of the room, until an unbalanced force changed my motion, caused me to stop, right? That's Newton's first law. Newton's second law relates to the acceleration of an object. It's two parts as well. The acceleration of an object is directly related to means it's a linear relationship. It means if this is bigger, then that is bigger. If this is to the right, then that's to the right. It's directly related to the net force. If you double the net force, the acceleration doubles. If you cut the net force in half, then the acceleration gets cut in half. If the net force is to the right, then the acceleration is to the right. If the net force is downwards, then the acceleration is downwards. So whatever happens to the net force also happens to the acceleration. That's what it means when we say it's directly related to, directly proportional to. The other aspect of it is that the acceleration of an object is inversely, what does that mean, inversely? One goes up, the other goes down, inversely related to the mass. If the mass goes up by a factor of 2, then the acceleration goes, Haley, if the mass goes up, if the mass is doubled, then the acceleration would be, by a factor of. If the mass is increased by a factor of 2, then the acceleration would decrease by a factor of 2. Good. So it's inversely related, inversely proportional. Mass goes up, acceleration goes down proportionately. Mass goes up by a factor of 17, acceleration goes down by a factor of, Peter? 17. Make sense? Okay, we're going to put that into a bit of an equation here. We're going to say that, kind of combine those two things. The acceleration, if it's directly related to the net force, then it will be equal to the net force on the top, inversely related to the mass on the bottom. So Newton's second law as an equation really becomes A is equal to F over m. Now, if we rearrange that to solve for F, and that's usually the way we end up seeing it written on a data sheet, solving for F, we say F is equal to m times A. JC, is force a vector or a scalar? How do you know that, JC? Yeah, has the arrow sign over top of it, right? Now, the other way that we can determine that force is a vector is that it's the product of a scalar and a vector. When you multiply a scalar and a vector together, you always get a vector. Okay? Vector equals a scalar times a vector. Listen, if the acceleration is directly related to the net force in the same direction as the net force, it has to be a vector, right? What are the units that we're going to use for mass here? Sarah, what are the units that we're going to use for mass? Not grams. Okay, you think in chemistry right now. Right? Do you take chemistry? In chemistry, you're going to use grams all the time, right? Because like things, usually when we're dealing with chemistry, we're dealing with small amounts of things, right? In physics, the standard unit that we use is not grams, but kilograms, right? Sarah, what do you think we're going to use for acceleration? Good. Meters per second squared. Now, does anybody have, or at least think they have, the units for the net force? JC?
Just gonna guess, but is it
No, that's a good guess, though. Joules would actually be energy. Okay, and we haven't talked about energy yet, but we will. Okay, that's a good guess. But it's not energy. Yep. It's newtons, yeah. So the units we're going to use for force are newtons, and we're going to abbreviate a newton by an N. All right, let's take a look at example 3.5 on page 149 of our book. It says, a lacrosse player exerts an average net horizontal force of 2.8 newtons. It says forwards, right? Didn't really need to say that because we always assume that the force is in the positive direction or whatever vector is in the positive direction until we're told otherwise here. So at a 0.14 kilogram lacrosse ball while running with it in the net of his stick, what's the average horizontal acceleration of the ball while it's in contact with the lacrosse net? McKenna, tell me something that I'm given here. One variable that I can write down as my given here. I'm sorry? Okay, so something is 2.8 newtons. What would that be? Would that be mass? Would that be force? Would that be acceleration? Would that be velocity? Good, that's the force, and specifically the net force. We'll just call the net force F. Okay? If we mean a force other than the total force, then we'll usually write it like an F1 or an FA or an FQ or some little subscript there. Good. So the net force is 2.8 newtons. Grayson, give me another thing that I've got or that I'm looking for here. Good. Are we in the right units here? 2.8 newtons and 0.14 kilograms? Yep. Yep, we are. Good. Maddie K, I'm looking for acceleration, right? If I'm looking for acceleration, what equation do you think I'm going to use there? Yeah, acceleration is equal to net force over the mass. We don't even have to rearrange this, do we? On our data sheet, though, be careful. It's stated F is equal to m times A. So if you look in your data sheet, you will have to rearrange it. F is 2.8 newtons. We divide that by 0.14 kilograms. Do the math there, and it's going to work out to be 20 units. Well, you could say meters per second squared because that's units for acceleration, right? What else could we do? Oh, a new set of units that we could use for acceleration. Okay, we don't have to, but can. Meters per second squared, or take a look up here. Meters per second squared, or? Yeah, Grayson? newtons per kilogram. I'm going to write down newtons per kilogram here, but you can absolutely say 20 meters per second squared. Either one of those would be absolutely correct. Okay, they mean exactly the same thing. All right? 1 newton per kilogram is the same thing as 1 meter per second squared. Most of you will probably use meters per second squared. That's fine. Good? So look, now we have, if you look at your data sheet, we had a group A equation, v equals d over t, and we had 5 group B equations, all those acceleration equations. Really now we have a 6th group B equation, right? Because anytime an object is accelerating, those other 5 equations still apply, but now we've got this one that also applies when the object is accelerating. Let's take a look at the 2 questions on page 149. All right, let's have a look specifically at question number 2 here. Nick, question number 2 says, a net force of 34 newtons acts forward on a curling stone. That means that F net for number 2 is equal to 34 newtons, causing it to accelerate at 1.8 meters per second squared. That's A, 1.8 meters per second squared. We're looking for the mass, right? What equation, Nick, are we going to use here to solve for the mass? Yeah, you could say A is equal to F over M, or you could say F is equal to M times A. Hey, let's go with the form that you gave me. A is equal to F over M. We're solving for mass here, right? Do you know how to get mass to the top here? Good, you're going to multiply it. So it becomes A times M equals F. Or you could say F is equal to M times A, right? And then we're going to take the A over by, Christian, we're going to take the A over by? You know how to take that A over? Okay, well, let's just look at this. I got to solve for M here. How do I take the A over to the other side? It's multiplied by M, so I'm going to take it over by? Divide. Right. So M is equal to F over A. Good. F is equal to 34 newtons. A is equal to 1.8 meters per second squared. And when I do the math there, 34 divided by 1.8, I assume I get 19, and the units, of course, would be kilograms. Or you could say newtons over meters over seconds squared, which would be an odd looking set of units for mass, but it would be correct. Right? One more, and then we're going to wrap it up for the day. This one, you're going to have to copy this one out. Sorry, I didn't photocopy it for you because it's just one example. This one says a 1,000 kilogram car moving at 72 kilometers per hour slows to a stop in 10 seconds. How much force, should say how much force was required to stop the car? You know what, I'm going to pull out the red pen here right now, and I'm going to draw attention to something just so I don't forget to deal with it later on. Nick?
See?
You're right. You're right, Jake, sorry. Yeah, that kilometers per hour thing, right? If I don't remember to convert that to meters per second, I'm going to get this question wrong. And sometimes it's useful to circle it in red to remind me to convert it later on. So what do I got here? I got a mass of 1,000 kilograms. What is that 72 kilometers per hour thing? What variable is that? Velocity. What velocity is it? Initial or final? That's going to be final, good. Sorry, initial should be, right? It's traveling at 72 kilometers per hour, and it slows to a stop. So, Jacob, if that's the initial, then what would the final be, Jacob?
0.
Right. By the way, we're going to convert that 72 kilometers per hour in meters per second. 72 times 1,000 divided by 3,600 gives me 20 meters per second. We're looking, time interval is 10 seconds here. We're looking for the force. So we're going to say F is equal to M times A, but we got a problem here. What is it? We don't have A. Good. Peter, what are we going to do to find A? Sorry? Yeah. Change in velocity over change in time. It's a group B problem, right? It involves acceleration. All of my group B equations, including the ones I learned in the last unit, are valid. So we're going to say delta V over delta T. That's 0 minus 20 over a time of 10. Gives me negative 2.0 meters per second squared. Good. It's negative. It should be because I've slowed down. That means that the force is 1,000 kilograms. The mass times negative 2.0, which gives me negative 2.0 times 10 to the 3, or negative 2,000 newtons. Now we got to start worrying about significant figures, right? Because we've written our first unit test. 2 digits. Final answer is 2 digits because this is 2 digits. This is 4, but this is 2, and this is 2. Final answer should be 2 digits. Should it be a negative value? If I'm moving in the positive direction, how do I slow down? Apply a? Alexis, if I'm moving in the positive direction, how do I slow down? I apply a pipe brake, but the force needs to be negative, right? If I'm moving positive, the force needs to be negative to slow me down. And remember one more thing here before we wrap it up. The acceleration is proportional to the force, which means if the acceleration is to the left, then the force must be to the left. Good? That is it.